All right, good afternoon, everyone. Y'all doing okay? Y'all ready?
Good morning.
Yep. Kind of morning still?
Hello.
Yeah.
Okay, so last class we started talking about chapter 2, the derivative, and we're starting out with the first section here, 2.1. And I have a bunch of pre-made notes about all of this, but I think I'm going to do this a little different. So if you want to look at these notes, you can look at it, you know, in Canvas, you can get these notes, but I'm going to do a slightly different approach today. So we're doing 2.1 derivatives and rates of change. I just want to start with an example. I think if we start with an example, things might make a little more sense as we work through it. So we're looking at a parabola here. It's x squared minus 3x plus 2. So I'm just going to take a quick little screenshot of this, and then we'll move it over and we'll start working with this thing. All right, so here it is. I'm going to write down the function here. This is f of x is x squared minus 3x plus 2. All right, so we should be very familiar with parabolas from college algebra. And what I want us to do is the following. I would like for us to find the average rate of change in f, in this function, on the interval, let's go 3 to 4. So 3, 4. Okay, so the first thing would be like, what does this mean, right? So what does it mean to find the average rate of change? So the average rate of change means if you go to the point, first you look at the x value 3. Okay, so let's look at that x value 3. That would be here on our graph, and then we have a point that corresponds to that. It looks like it has a value of 2. So does everyone agree that at f of 3, the function is 2? Yes? Okay, now let's look at the next endpoint. The next endpoint is this x, 4. Okay, so if we let x be 4, you know what, I didn't do a good enough screenshot here. Let's see. At 4, we're at 6. Okay, so I'll go back here and I'll just fill it in. So up here, let's say at 4, when we plug in 4, we get a value of 6 here. So we know that when we plug 4 into the function, we get 6. So the average rate of change of the function is simply the slope of the line that connects those 2 points together. So if you were to connect these two with a straight line, these 2 points, that slope, whatever the slope is, would be the average rate of change. All right? So you have to remember how we got slopes back in college algebra. When we talked about the slope of a line, we said it was rise over run. And in this case, the rise would be the distance from here to here. That's our rise. And do you all agree that that would just be the 2 y coordinates subtracted? In other words, you know, whatever the y coordinate is of this point, let's actually write this point out as an ordered pair. This has as an ordered pair 4 for x and 6 for y. And this point here is 3, 2. So do you all agree that the rise would be the difference of the y coordinates, right?
Yeah.
So that should just be what, 6 minus 2? So we rise by 4, yes? And then how much do we run by? So the run is the distance, kind of running out of space here, but the run is that distance right there. And that should be the difference of what?
The x values.
The x value.
Right? Okay. So the x value of the second point is 4. and the first point was 3. And so we get, let's see, 6 minus 2, that's 4, and then over 1, so we get 4. So the slope of that line is 4. And so that would be the average rate of change. So between 3 and 4 on the graph, the average rate of change was 4. Any questions on that? No?
Why do we call this average rate of slope, average rate of change? Why can't we just call it just a slope of two lines?
Well, it is. It is the slope of the line connecting those 2 points. But the reason it's the average rate of change is because, let me show you a different example, just a real quick different example that might help explain this. Let's say that this is time. Let's say that's in hours. And let's say this is miles. So this is a distance, right? Measured in miles. So you're going to take a road trip, right? So you start driving your car. So when you start, time is 0. You have not gone anywhere. You've driven 0 miles. And then you start your road trip, and maybe, you're driving, you speed up, slow down, whatever. And then you get to the final destination, wherever you're going. Let's say you traveled 200 miles on this road trip. And let's say it took you 4 hours to do that. Okay? The average rate of change is the slope of the line connecting these two. Okay, so let's figure out what that would be. So what's our rise here? So the slope of this line would be, what's the rise?
200.
200, right? Because this is like the point 4,200. We traveled for 4 hours, we went 200 miles. This is the 0.00. So the rise should be 200, right? 200, take away the height of this point, which is nothing, over the run, right? The run, which would be here, what?
4.
4, take away 0, so just 4, right? So you get 200 over 4, which is
50.
50. Now, 50 what? What unit do you think this would be?
Miles per hour.
Miles per hour. So we have miles here and hours here, so this would be miles per hour. So what does that 50 miles per hour mean? It means that on this trip, your average rate of change, the average speed you were traveling was 50 miles per hour. Now, does that mean that every single moment in time you were traveling 50 miles an hour? No.
No.
You sped up, slowed down. Sometimes you were driving 30 miles an hour. Sometimes you were driving 85. It just depends, right? But your average rate of change, in this case, would be 50. Does that help kind of explain why we need to call it an average rate of change?
Yes, sir. Thank
Okay. Any other questions on that? So let's stick with this example just while we've got it up here. We know that on this particular trip, the average rate of change was 50 miles an hour. We could do that for any interval. So like I could ask you, look at the last hour of your trip, okay? If you look at between 3 and 4 hours, if we just look there, that's 3 hours. Then if I find the slope of that line, that's going to give me the average rate of change or the average speed in the last hour of the trip. Does that make sense? In the last hour, just the last hour. Or I could have said, let's look between, let's say, 2 hours and 3 hours. So I go and I put a dot here, and then I put my dot here, and I connect those with the line, and that would have a different slope, right? All these little lines have different slopes. So between the second and third hour, I would have a different average speed, right? All of these questions about average speed are problems we could answer because they're simple algebra problems. Rise over run, just a couple of numbers you subtract, divide, you're done. The calculus question is this. You see this point in time right here? I'm just gonna put a question mark there. I'll highlight it in blue. You see that point in time? I would like to know at that exact moment in time, right there, when you were right there, on your trip, driving down the road, how fast were you going? Not an average rate of change, but the speed at that instant in time. Do you see the difference between those two questions?
Yes.
Yes, sir.
Yes. So average rate of change requires 2 points and you have an interval, as opposed to me asking you what's going on here, which we call the instantaneous rate of change. Big difference. This one down here is the average rate of change, because I gave you 2 endpoints, right? 2 points to figure out, and then you just gave me the slope of the tangent line through those 2 points. Here, we're asking for the instantaneous rate of change, and that's a problem. That is a major problem, because if you're talking about the speed at an instant, you don't have 2 points, which means, and this is the theme of calculus, I've told you this, if you're just looking at 1 point, your rise must be nothing, because at 1 point you're not going up at all or down. And your run must also be 0, right? Because you're not moving left or right. So we get 0 to 0, which traditionally is a problem, but because we have the limit now, we should be able to address this. Does that give everybody kind of like a broad view of where we're trying to head here? We're trying to get to this. Can you talk about the speed of something at an instant as opposed to an average? Yes? Questions? Okay, so let's go back up to this picture. I gave you this parabola. I said, hey, find the average rate of change on the interval 3, 4. Okay, and we found it, and the answer was 4. New question. Take the same graph. And here's what I want us to do. I would like for us to find the average rate of change, not on the interval 3, 4, but on the interval 3, 3.1. So what have I done here? I've said, okay, I'm going to go to 3, I'm going to go up, and then I have a dot, right? And then I'm just going to go a little bit to the right of it, just slightly to the right, to 3.1. Now I'm going to exaggerate this to make it easier for me to draw it. 3.1 is a little bit to the right of it, isn't it? Then I go up and I have another dot right here. And so what we're trying to find is the slope of the line that connects those two together. Okay, the question is, what is that slope? Right? So we just need to know the rise over run. But to do the rise over run, I need the 2 points. I need to know what they are. So let's figure out what these 2 points are. First, let's figure out what happens at 3. If we plug 3 in, don't we already know what we get when we plug in 3? Which is 2, right?
Yes.
Okay, now that means I have a point. The point is the point 3, 2. And that's this point right here. Okay, and then the other point, I need to plug in 3.1. And I saw Benjamin break out his calculator, good, because we'll need the calculator to just plug 3.1 into the function. Does anyone have that yet? I'll tell you what I get. I get about, well, I get 2.31 exactly there.
I got the same.
You got the same? Okay, good. So that means we have a point on our graph, 3.1, 2.31. Go with me? So let's talk about the slope. The slope of this should be rise over run. The rise is always the difference of the y coordinates, right? So I'm going to take this y coordinate here and subtract the green one. So I'm going to take 2.31 and subtract 2. Then I'm going to divide that by the 3.1 minus the 3. And let's just see what we get here. You should get 0.31 over 0.1. So you should just get 3.1. So you could verify that on your own calculator. But do you all believe that? You okay with that?
Yeah.
So think about the question I asked before this. Before this, I said, hey, what was the average rate of change between 3 and 4? And the answer was what? 4, right? But the average rate of change between 3 and 3.1 is actually 3.1, right? That's what it is.
Is there a reason why there's a relationship between the last number?
No, it's not. There's no, yeah, it's a coincidence, actually.
Okay.
The fact that this is 3.1 and this was 3.1 and there's a 3.1 there, don't worry. No, it's just a coincidence. Okay, we good? We're gonna do another one. Same thing.
Is this, I have a question. Is this all we have to do or does it get harder?
Oh, it gets harder.
Oh, great.
For sure.
No, but see, here's the thing. We're trying to build up. We're trying to build up the understanding of what we're going to be doing. All right. I'm trying to motivate the idea here. So remember, what the ultimate goal here is to say, hey, at 3 right there, what's the instantaneous rate of change? That's the goal. But all we really know how to do at this point is find the average rate of change, which requires us, you know, we could pick 3 and 4, or we could pick 3 and 3.1. What would be another point that I could pick that would be a little bit to the right of 3, that's even closer than 3.1?
3.01.
You could go 3.01, right? What would be even closer?
You could add a lot of zeros.
Yeah, let's
in
do
there.
a couple of them. Let's do like 3.0001. Let's do 3 zeros and a 1. Do y'all agree we're pretty close to 3 now?
Yes, sir.
We're pretty close. So let's try it. All right, we already know when we plug 3 in that we get 2. We've done that already. Now, if we plug 3.0001 and do this into our calculator, I'm getting that this is 2.00030001. Does anyone else get that? I see Benjamin cranking away there.
Yes.
No? Okay, so the slope should be the rise over run. So what I'll do is I'll take the y coordinate. Well, you know, I didn't write these down as points, but I'll do that just to have it here. 3.0001, and then when we plugged it in, we got 2.00030001. Sorry, I ran out of room there. So when you do the rise, it's going to be the 2.00030001 minus 2 over the run, which is 3.0001 minus 3, which is going to give us make sure I did not type that in right. 0.00030001 divided by 0.0001. I get 3.0001.
Hey, Professor, how did you get that 2.003001?
How did I get that? I plugged 3.0001 into the function.
Okay,
So I squared it, I subtracted 3 times it, and I added 2.
got
I
it.
did all that on my calculator though. Is that okay? All right. So, okay, so what's happening then? Look, when we went from 3 to 4, right? The slope of that line was 4. When we went and did the one before this, where we were at 3.1 and did that point and did that little slope there, the answer was 3.1. And when we got even closer to 3, right? Even closer, which I'd have to like zoom in on this to see it, right? when we were real close here at 3.0001, the slope looks like it's really close to 3, isn't it? So do you see the trend in these 3 examples? The first slope we got was 4. The next one we got was 3.1. The next one we got is 3.0001. What does it look like it's trending towards?
3.
3, right? Maybe it's 3. Maybe it's just 3. You go with me? So, maybe there's a way we can do this and really convince ourselves that this is true. So we're going to do one more. Okay, ready? One more. But we're going to do it in a completely different way. Well, not completely different. I'm going to kind of throw a curveball at you here. So I really, really want to know, okay, the ultimate goal here is to try and figure out what is happening at 3. Do we have an instantaneous rate of change there? So what I've been doing is picking a point a little bit to the right of 3, haven't I? Started with 4, then I did 3.1, then I did 3.0001. So watch this. Here's what I'm gonna do. I'm gonna be clever. In math, we like to be clever. Makes us feel good about ourselves. So here we go. I would like for us to pick the point 3 and not 3.01 or anything like that. I'm just going to call this point X. Okay? I'm just going to call it X. Now, I'm going to label that X over here. And would you all agree that it lands somewhere up here? I don't know where because I don't know what X is, right? X is just left as an unknown. Y'all okay with that idea? Okay, so let's just follow the same procedure. We would like to know the slope of the line through those two. So we need to know that slope. All right, well, let's go ahead.
Do you pick any number for X? You just chose whatever?
I'm not even gonna, so instead of picking 4 or 3.1 or 3.001, I'm gonna leave it as just a variable. Just
Okay.
gonna leave it as X, okay? You'll see where this is going in just a second, all right? So let's talk about the slope. It's rise over run, which means we need the 2 points, don't we? We need the 2 points. Now, one of them we already know. F of 3 gives us 2, and so that's the point 32, right? But what about the next point, right? This one is the point 32, but what's the other point? What's this point right here?
The equation itself, right?
Yeah, so what the question is, what happens when we plug that number into it? And the number we're plugging in is X, so it's unknown, right? So we're really saying, all right, what is f of X? What happens when you plug X into the function? Well, it squares it, adds, subtracts 3 times it and adds 2. Isn't that what happens when you plug X into the function? So critical point here, written as an ordered pair, just
Can
like we did here. You plug in 3, you plug in 3, it spits out 2. Go ahead, what?
I was saying, can we factor out this?
We're not going to do that yet. We might do some factoring in a moment. Right now, we're just trying to see what does this represent as an ordered pair on, you know, on this graph. If I write this as a number, right, or an ordered pair, what would it look like? So what's the input? What am I plugging in here?
Itself.
X itself, right? Okay,
Yeah.
and then what comes out?
The equation.
Yeah, the equation.
It's called like the identity function or something like that.
If this was X comma X, it would be the identity. Right. I really want to make sure everyone understands what we're doing here. I want to try and find the rise over run. So I need 2 points. The first point is easy because it's just plug in 3, it spits out 2. The second point, I'm not telling you what it is. I'm just saying it's X. And so when you plug X in, it's going to spit out whatever the function does to X, which is, well, it's the definition of the function, isn't it? X squared minus 3x plus 2. We good with that or not?
Yeah, we're good.
Okay, now, what were we doing before? To find the rise, didn't we do the difference of the y coordinates? Didn't we do the difference of the y coordinates? Okay, so I'm going to take, let's start with this y coordinate, and I'm going to subtract from it that y coordinate. Let's do that. So I'm going to take x squared minus 3x plus 2, and I'm going to subtract 2. Y'all see where I'm getting that? This right here, that's that, and then I'm taking away 2 over, now this one right here is just this x coordinate, which is what? This x coordinate, it's just x, right? So I'm going to take x and subtract from it 3.
Mm.
Is everyone okay with that? Are there any questions? Let's clean this up algebraically. These twos cancel. So here's what we're left with. X squared minus 3x over x minus 3. All right. So let's try and wrap our heads around what we just did. All right. We are saying here that if you want to know the slope of the line, right, M, if you would like to know the slope of that line, where 3 is the left point, right, and the right endpoint is x, then the slope of that line will be x squared minus 3x divided by x minus 3. We've come up with like a formula, right? This is a formula that will work now for any x. So let's try. Didn't we use 4 earlier? Didn't we use 4 for the right endpoint?
Yep.
What happens if we plug
Yeah,
4 in?
early.
What happens if we plug 4 in here? 4 squared is
16,
16 minus 3 times
12.
12, and then that would be divided by 4 minus 3.
Yep.
Would be 1. So we get 4, wouldn't we?
Mm-hmm.
It works, doesn't it? And it would work for 3.1, and it would work for 3.0001, right? All 3 of those it would work for.
So it wasn't a coincidence before.
It's a coincidence that we still had 3.1 as our y and as our slope. It doesn't always have to be that way.
Yeah, it would depend on the equation, right?
It depends on the function completely, yes.
Yeah.
Okay, now here's the big eureka type big moment now. We need to make this a calculus problem.
What if we put a different number besides those, like 3, 4, and 3 or 3.11? Let's say just like we put a 5 or 6.
Yeah, it would work.
Yeah.
Okay.
You just simplify that and make it just x eventually.
So you're almost there. Yes. Hold on. We're getting very close. I want you to think about this though. The ultimate goal was for us to look at 3, to go up to that point and ask ourselves, what's the instantaneous rate of change, right? What's happening at that instant? Which means you're no longer allowed to have 2 points. You can only have 1 point, and you can't come up with the slope if you only have 1 point. However, I could get better and better answers, like closer and closer answers, if I allow x to do what?
Move closer to
The infinite?
Okay, who said that? Move closer. Who said that?
Austin
Austin, move closer to what?
to 3.
Move closer to 3. Think about this x value. Right now, it's just arbitrary. But wouldn't I love to move that x really, really close to 3? Wouldn't I like to do that? The closer that x gets to 3, the better and better our guess is going to be here as to what the slope is. Now, how do we do in this class? What have we learned? If we ever want to let something get close to something, what do we use?
A limit.
The limit. The limit. So why don't we do that? Why don't we just say, hey, look, this is kind of the master formula that we just came up with for this particular problem. Why don't we take the limit now and let's let x approach 3 of that expression.
Does it matter which way x approaches 3?
It does not. Good question. It does not, because when I drew this x, I drew it on the right-hand side, didn't I? But it could very well be that the x is on the left-hand side. What we're going to do is we're going to take a limit and let x approach 3. So we're basically, we don't care which side we're coming in from. Good point to bring up there, Natalie. Okay, so here we go. Here's where we are. And let's see. Claire, are you here? Claire. Claire. I see Claire. All right. So here's what's going to happen. If I call on you multiple times, right? If I call on you multiple times and you don't respond multiple times and you're just kind of here, like logged in but not present, I'm just going to kick you out of the room. Okay. So, but I mean, first time is okay, but if it happens a couple of times, it's going to be a problem for me. Okay. All right. Now, Laura,
I
is
have a
Laura here?
question.
Oh yeah, question?
So if we're gonna find the limit, do we still follow the rules? Like whenever we find a limit, like using direct substitution first and da.
Yep, exactly. So now what we have is a calculus problem, right? We're gonna let x approach 3, we're gonna see what happens. And you know, since you brought it up, Danielle, what happens when we do direct substitution here?
It might go to, is it gonna be 0, 0?
It is 0 over 0. It is 0 over 0. So if it's 0 over 0, we're gonna have to do something, right? So Danielle, you have any idea what we could do here? Some algebra, some trick or something to make that not be a
Yes.
problem? What do you got?
Right. So I would try and then I would try and factor out the numerator and see what I can do.
You can pull an x out, right?
Mm-hmm.
So if you pull an x out, you get x minus 3. And on the bottom, you have x minus 3. And hey, voila, they cancel, don't they?
Wow.
And then that becomes limit x approaches 3. I'm laughing because I heard a wow. Was that you, Danielle?
No.
No,
It
no,
was
but
not
it
actually.
came from your audio, no?
No.
No?
that Brian?
That was me. I
Oh.
like to say a bunch of random stuff when I'm muted, and I forgot to mute.
Oh, okay. I was gonna say, whoever said wow is probably not referring to what we're doing right now.
Actually, I was.
Okay, good.
It was.
Okay, good. All right. I thought it was someone in the background with Danielle, so I was like, okay, whoever's over there, they're not watching what we're doing. Because, all right. So here we go. So do y'all see what happens now when we take this limit? Let x go to 3. What's the answer? 3.
Yeah.
And look, that's what was happening, right? Remember, we said that when we first did this, right? When we first did this, we got 4, right? And then the second time we did it, we got 3.1, then we got 3.00001, and it looked like it was getting closer to 3, didn't it? And what we just showed is that it does in fact approach 3. Okay? So it looks like if I want to do this for like a different point, like maybe now I'm interested in the instantaneous rate of change over here at -1 instead. So I'd like to know right there, like, what's the instantaneous rate of change? Couldn't I just kind of do the same thing, but not do a bunch of different points, just start with x to begin with and let x approach that? And just kind of like not waste my time just guessing? That is the idea of the derivative. That is it right there. It's a way of finding the instantaneous rate of change of a function at some given point by applying a limit to the rise over run formula. That's all it is. I hope that makes a little sense. We're gonna start over. We're gonna bring the graph in here again, and we're gonna try it with a different point. All right.
I have a question.
Yes.
How come you had to take the limit? Like, why couldn't you just continue simplifying the equation for the slope and just know that it would be 3?
In that particular problem, it would have, right?
Mm-hmm.
If you would have factored and canceled, right?
Yeah.
Is that what you're saying? And then you would have got your answer as 3. Oh, you know what? Here's a way. I think I know what you're talking about. This is a very good point that Laura is bringing up. This is extremely important, all right? And it's overlooked a lot of times. Let me do it this way. I think this is more interesting. Okay, clear your minds for just a second, all right? I'm going to give you 2 functions. I want you to think about them. First function is f of x equals 1. And the second function I'm going to give you is g of x equals x minus 2 over x minus 2. The question for you is, are these the same functions?
Yes.
Yes.
Yeah.
Yes?
If you're not talking about like f of x and g of x and just like what they're equal to, then yeah.
So y'all think so?
Yes.
Yes? They're identical.
Yes.
Their end value is identical.
Okay, so their outputs are identical.
Mhm.
I disagree. And that is
Wouldn't it be?
not correct. So they are not the same functions. They're almost the same functions. They're almost. Because if you plug in any value you want for this one, like over here, like let's say I plug in 4, right? I'm gonna get 1. It doesn't matter what I plug in, right? It's gonna spit out 1 no matter what. Over here, if I plug in 4, it's going to spit out, let's see, 4 minus 2 over 4 minus 2. This is going to be 2 over 2, and that's going to give me 1. And that would have worked for any value of x except what?
0.
Except 2, right? At the bottom, right?
Except
Okay,
2.
yeah, that was going to be my question.
So
Like,
look, f of 2 is still 1 because f always just spits 1 out. But what if you try and plug 2 into g? You get 2 minus 2 over 2
we're going to
minus
get 0 over 0.
You're
We
gonna
have to
get
do
0
our
over 0.
algebra.
And that's undefined, right? So to get to your point, Laura asked this question, which was a very good question. Back when we were doing this problem right here, why not just at this point simplify it and then plug 3 in? And we would have got the same answer, never even do a limit. Okay, that was, I think, what Laura was saying. Here's why you can't do that. Because when you're given an expression like this, I know everyone in here is very tempted to just turn that into 1. Just say, oh, this cancels with this, right? That's what everyone is tempted to say. But what you aren't taught in college algebra, it's not emphasized enough, is that anytime you cancel 2 factors like that, you have to make me a promise, okay? This is what they don't tell you in college algebra. You have a little asterisk on the side. You know how the little asterisk at the bottom of a form like tells you something? Okay. Anytime you cancel 2 factors like that, there's a little asterisk that says, but x better not be 2. In other words, it's saying, yes, you are allowed to cancel these, but you better not try and plug 2 in then afterward, because if you try and plug in 2, then that canceling isn't legal. Does that make sense? So
Yes.
even though algebraically you want to turn this into a 1, there's a catch.
Is there like a PEMDAS you can follow for when you can do that?
You can never cancel factors without making a promise that you won't ever let the x value be whatever those factors would make those factors 0. Let me give you another example. If I had like x squared minus 3x minus 4 over x minus 3, let's just say, and I factored the numerator out. Let me make that minus 4. If I factor the numerator out like this, okay, and then you go, oh yeah, hey, look, those cancel. I agree, they cancel, but asterisk, x can never be 4 now. So you're not allowed to then go and plug 4 into this later. You're not allowed to, because this right here, if 4 goes in, then it would have been 0 over 0. So you're cheating, you're canceling to get rid of a problem that is there. The problem is there. I mean, x minus 2 over x minus 2 is there. I hope this is making sense. That when you're given an expression, you cancel factors. Like, you're not free to do it without, you know, I'm going to hold, now you're being held to a condition. You've put a condition on things now. Whereas the one on the left, there's no condition. The answer is 1, doesn't matter which plug in. So let me just show you real quick what these graphs would look like. Here's the graph of f. It's just a flat line, okay? That's what f would look like. It's 1 unit high, there it is. Here's what g would look like. Same thing, except when you get to 2, g has a hole. So there's a hole in g where f doesn't have a hole. All right, that's the difference between those two functions. So Laura, to your point, to your question, the reason I did not do anything here and factor out and cancel 3s earlier is because if I would have, then I would not have been allowed to plug 3 in, right? But then you might ask, wait a minute, didn't we just plug 3 in here to get the answer? Didn't we? Well, did we? When we take a limit, are we saying that x is going to be 3?
No, it's approaching 3.
Approaching 3. And so what we're saying is that x approaches 3, this approaches 3. We're getting closer and closer and closer to 3. How close? As close as you ever want to get. All right.
I have a question.
Yeah.
When you're putting in your rise over run to find out the slope, do you always subtract the opposite value?
Subtract.
Like when you put in the x squared minus 3x plus 2 minus 2, are you always going to subtract the x's and the y's?
You always, well, whatever, you could start with this point, and then this will be like your, how do I say this? Whichever one you choose, okay, you can choose either one. You're going to take the y coordinate of one of them and subtract the other one. And then the x coordinate of one of them and subtract the other one. But you have to be consistent. Like if you're going to choose this one and subtract that, then you have to do this one, subtract that. If you do this one, subtract 2, then you have to do this one, subtract 3. Is that your question?
Yeah, it does.
Okay. Let me do another problem, okay? I mean, not another problem. Let's do the same problem.
Hey, Professor,
Yes.
since we're doing this limit, so every single time we say it's approaching 3, but we are not sure, like, is it exactly 3? So will there be anything that could like prove us it is exactly 3, like in future?
Well, we just did. Okay, so these are
But
great
isn't that
questions.
But
But-
isn't that an approaching thing? It's just not like exactly, okay, like it is 3.
Okay, how can I say this in a way that will make sense? This is go ahead.
I thought that I was thinking that when you had said anytime we take the limit, we don't care what's happening at that number. We want to know what's happening around or what we're doing, so we couldn't ever be 3, right?
Yeah.
That's.
But I think the
I don't know if
question that's being asked is, then if we can't ever get to 3, then how can we ever prove that the answer in this case was 3? Is that, am I?
Right, that was the question.
Okay, okay, so you're asking a very difficult question to answer easily, because when I'm showing you calculus right now, right? This is your first introduction to limits and derivatives. We have the biggest problem that we have right now is the idea of closeness. And I brought this up, I think, earlier in the semester. Like, you know, are we close to one another right now? Would you consider us close? Not close like how you feel about me, like in your heart. I'm talking about like physical distance between us. Are we close?
No, sadly.
Well, so it's relative, right? Like compared to the sun, y'all are very close to me. It doesn't matter where you are, right? You're all significantly closer to me than the sun is to me. But you could also say that the sun is very close to you also relative to the nearest other galaxy, right? So, I mean, everything is relative. So what we run into in a class like this is a problem with that word. We're getting closer and closer and closer, but we're never getting there. And there's only one way around that, and that is to give you the precise, exact mathematical definition of a limit. See, because mathematicians don't work with closeness. Like, it doesn't work for us, right? We have to have something more precise. And so there is a very, very precise definition for the limit. And that would answer Dilpreet's question, which is, well, then how do we know? Well, if you use the precise definition for the limit, then you can prove that the answer is 3, okay? But I'll write the definition down and I'll show it to you, and then you'll see why we're not talking about it. All right, so here's what it is. So the limit as x approaches a of f of x equals L, what that means mathematically is that, I'm going to write it the way a mathematician would write this, okay? So you're going to look at it and go, what the hell? Okay, it means that for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of f of x, absolute value of x minus a is less than delta, then that forces the absolute value of f of x minus L to be less than epsilon. That is the precise definition of the limit of a function. All right. And what there's no way I can explain this to you because there's too much here. Okay. You have to understand logic, how proofs work. Okay. I'm showing it to you because this is the trouble in Cal 1 is how far down the rabbit hole do we want to go? Can we accept the idea of close and be happy with it or not? If we can't accept it, then we have to go down this rabbit hole, which we don't do because then like 90% of you are going to fail the class. If we do delta epsilon proofs, that's what this is. Okay, so we don't go down that way. But let me put it this way. This is the easiest way I can put it. I'm claiming to you right now that the answer is 3. Okay? For this problem, I'm claiming that the answer is 3. But Dilpreet doesn't believe me. Okay? Dilpreet doesn't believe me. He's like, no, I don't think it's 3. And I'll say, well, how close? I'll say, how close do you want me to get to 3? And so Dilpreet goes, well, I want you to be within 3.0000000000001. That's how close I want you to be to 3. So what I do is I will pick a number. Let me erase this. I will pick a number. Here's 3. I will pick a number really close to 3. I don't know what it is. I could find it though. And I could plug it into all this stuff that we did, and I would get an answer that was as close as Dilpreet wanted me to be. Okay. And then Dilpreet goes, well, wait a minute, I changed my mind. So I'm going to do 3.000, and she's going to put 1,000,000 zeros and then a 1. And I'll say, okay. And then I will go find the number that gets me that close. And if I can do that for every number that she ever gives me, then the limit is 3. And that's what this definition is saying. It's saying for every number that Dilpreet gives me, there exists some little window that I can create so that as long as the value between 3 and the number I pick is smaller than that little window, then I guarantee that the value that I'm saying it goes to, 3, and the value that Dilpreet wants me to go to will be smaller than that little number she gave me. Now look, I mean, it's hard to follow, okay? And you're not going to be tested on this, of course. But with that, we can say it's 3. I hope that satisfies your curiosity.
It does.
Okay. So if you are really interested in this sort of thing, I recommend that you take some, finish up more math class. You have to get into like proof courses, theorem proving courses. So you basically have to be a math major to actually get into proofs. And that's where it starts to get really like you have to come back and do all the calculus again precisely. Okay, we're a little off topic. Let's keep going, okay?
I sent you a question in the chat real quick.
What?
I sent you a question in the chat. Is that okay?
Yeah, okay, so I'm gonna do something different. I'm gonna use the same function, all right? But everything I've been talking about, we've been looking at what's happening at 3, right? Let's just do a different value. So I want us to look at what's happening at -1. So the question is, find not the average rate of change, the instantaneous rate of change of f at x equals -1. Okay. I'll erase this since this is not necessary. Okay, so we're going to do the same thing we did before. We're going to look at the interval. We're going to go -1 and then x. So I'm going to be picking some value over here, x. I don't know what it is, and plugging it in and getting some value there, right? And then we have to do rise over run, but we need 2 points. So who wants to give me the first point? The easy one. What am I going to do to get the first point, which is the point here in green? What am I doing?
Would you plug it into the formula fx equals x squared minus 3x plus 2?
Yeah, plug what in there?
-1.
-1.
Yeah, -1. So let's just plug -1 in there and let's see what we get. Okay, so we plug -1 there, we square -1 minus 3 times -1 plus 2. Let's see what we get here. 1 plus 4 plus 2. We get 7. So that means we have a point, right? It's the point -1, 7.
Isn't that 6?
1. Oh, why? Yeah, that's, sorry. Brain fart. Okay, right here. This should be -3 or +3. You see what I did? I added them up. And then that should be 6. Who said that? Who caught that?
It was me.
Thank you. Thank you, Natalie. Yeah, if you ever see something ridiculous like that, just let me know. We're all humans, right?
Maybe.
Maybe. All right, so everyone good? That's this point right here. Now we need this point. So what do you think, Cody?
I'm sorry, which point do we need again?
We need, now I need the point, this one here. I need to know what that one is as an ordered pair.
Oh, yes, you would need, it would be.
What are we plugging in to the function?
Oh, 2?
No, we plugged in -1 for the left endpoint. Our right endpoint is,
Our right endpoint would be, well, it'd be anything greater than -1, so.
yeah, but we want it to be arbitrary, right?
Oh, 5?
We could pick 5, and we could pick 2, we could pick 0. But we're trying to make it arbitrary so that we can create a formula. So we're going to leave it as what? Someone help Cody out.
When do we do the X thing again? We would,
We're just
because
gonna
that's
leave it
a
as that.
coordinate.
Yep, we're just going to leave it as X. Okay. What we don't want to do is put a number in there and then have to come back later and pick a number that's even closer and then a number that's even closer. We're just going to use X right off the bat. And then from there, now if we plug that into the function, we just get the function, don't we?
Yes.
Okay. So that means as an ordered pair, you plug in X and you get X squared minus 3X plus 2. All right. Gage, are you with us?
Yes, I'm here.
Okay, Gage. So now that I've got 2 points, what am I going to calculate?
What's it called? The rate of change, right?
Yep, the rate of change, which is simply just the what?
What do you mean, like
what
subtracting
over what?
Subtracting the.
Yeah. Okay, so it's rise over run, right?
Rise over run, yes.
And the rise will be subtracting what from what? So what do you want me to start with?
So the X squared minus 3X plus 2. and then
And
minus the 6.
subtract the 6. Good. Anyone have
We
a question?
subtract, yes. And then the bottom would be the x subtracted the -1.
Perfect. Subtract -1. So isn't that going to be an add at some point?
Yes.
Okay, does everyone see what we've done? Good job, Gage.
Mhm.
So we've got the 2 points. Now we're going to do rise over run. So we do this one minus that one over this one minus this one. That should give us our rise over run. And now here's where we are. Now we keep going and clean it up. We get x squared minus 3x. On top we have -4, and then on the bottom we have x plus 1. Okay, and here is the big point where we're like, okay, now this becomes calculus. Elise? Is Elise here? Hey, there you are. I'm saying that right?
Yes.
No, I'm not. Am I saying your name right? Yeah, Elise? Okay. All right, Elise. What now? How do you make this a calculus problem now?
While factoring out the numerator?
So you're, okay, so you're already wanting to factor, right? That's what you're, okay. But to make it calculus and to be able to talk about the instantaneous rate of change, we need that x to basically slide over and try and be closer to this, right? So what do we use to do that?
You take the limit as x approaches -1.
Very good.
That.
So, good, perfect. So everyone see that. What we're going to do now that we have this expression is we're going to take the limit as x approaches -1 of this. Okay. Now, at least when we do that, can you tell what's going to happen if we plug -1 in? Any idea what that limit's going to turn into? It'll be 0 over 0. All right, which isn't a problem because we can handle that now. And Elise suggested that we factor the numerator, I think, right? So I'm not showing this, everyone. I'm not showing this, but if you do the limit, this will go to 0 and this will go to 0. That's going to be bad. And so we have to do some algebra. So factoring of the numerator becomes x, let's see, minus 4x plus 1. And the denominator is x plus 1. And now our x plus 1s cancel. Last thing, and Elise, I'm going to call on you again because I just realized I've only called on you, I think, once.
Yeah.
Okay, that's because I think I didn't have you on my roster initially, but you're down here, but I, for some reason, overlooked you. So I need to just make sure I fix that. Okay. So Elise, we can do the factoring and then cancel, right? And then there's a little asterisk right over here that says, because we canceled that, right, x can't be -1. But we're going to take a limit, aren't we? And when we take a limit, is x actually going to be -1?
No.
No, it's just going to get close, right? So tell me what happens to this now when you let x approach -1. What does this all become?
-5.
-5. So you're just plugging -1 in there. Basically, it's becoming -5. Now we're saying it's approaching -5. Very good, Elise, you're done. So we're saying that as you get closer and closer, the slope of this line should be getting closer and closer to -5. And if we go back up here and look at it, I'm going to go back to the original graph. Here. So if I go and I plot the point, what was it, -1, 6? Yeah, there's the point, right? That's the point on the graph. What we are saying right now is that if you were to take the instantaneous rate of change at that point, the slope of the line that would go through that point, like that. We talked about that last class. We called it tangent line. I haven't talked about that yet today, but oh shit. What happened? Come back to me. I just like deleted everything. Oops. Oh well, let me try it again. There
May I
we go.
ask a question? I have
Go
a
ahead.
question. So can we do, like, whenever we're trying to do this, can we use it as like a rule of thumb of using that formula of y2 minus y1, you know, equals slope x2 minus y1?
Mm-hmm.
Like we're going to use that every time.
Yep. I think we've done enough now where I think it's time to generalize this and come up with the master formula. I think it's time. I'm hoping that I've shown enough that people understand what we're trying to do. Okay, hopefully. What we did was we had a point that we started with, right? In this case, it was -1. Then we picked some point next to it, x. We figured out what those 2 points were, like as ordered pairs. Then we just calculated rise over run, and then we took a limit at the very end. That's what we did, right? Okay, let's see if we can't put this all together now into a general formula. Here it is. So clear your minds, whatever you need to do to clear your mind right now. Let's start out with the general picture. Okay, so this is a big deal right here. Let's say we have some function, call it f, all right? And let's say that we're interested in finding out what's happening here at A. We want to know at this point right here, the question is, what is the instantaneous rate of change of this function at x equals a? Okay, that is the ultimate question right here. That's what we're trying to ask. Okay. Now, I've told you that this is the function f, but I haven't told you what it is, right? Like I didn't tell you it was like x squared minus 3x plus 2. It's just a general function, isn't it? You don't know what it is. Yes? So what we're going to do now is we're going to pick a point next to it. I don't know, right here. We'll call it x. And we'll put that in there. And that'll be another point, won't it? Then we're going to find the slope connecting these two together. And then we're going to take a limit to move that point x closer to the a. So let's start talking about the points themselves. Maybe somebody here can help me. How about Austin? Are you there?
Yes, sir.
I'm just trying to figure out here what this ordered pair would be. This point right here, what would it be as an ordered pair?
For A?
Yep. Mhm. So what's the x coordinate?
A.
Okay. And then what's the y coordinate?
Would it just be f of A?
Yeah, because I'm not giving you, I'm not telling you the exact function, right? So all you can tell me is that, well, it's whatever you would get when you plug a in. See, if I actually gave you the function, then you could tell me what that is, right?
Right.
Okay, good. So is everyone clear on that? Like previously, this was just like the number 3, and then we plugged the number 3 in and got an answer, like 3, and this was 2, or -1, and that was 6, or something like that. But in general, we don't know this right now. How about this other point? Someone else want to tell me what that point would be?
Isn't it going to
Well,
be?
wouldn't that be the same thing except the x?
Yeah, it's the same thing with the x. It's x and then f of x, right? It's the x coordinate is x, the y coordinate is whatever you get when you plug x into the function. Danielle, is there a question?
Yeah, is it going to be like f of x minus f of a? Is that?
That's our next step. That's our next step.
Okay.
We've got our 2 points, right? And now we want to know the slope. So the slope, what we do is rise over run. And to do rise over run, we're going to take, let's say, this one right here and subtract that one. That's what I think Gage did the last problem, right? Gage, was that you who did that?
Yes, I think so. Yeah.
Okay, so it's the same principle, right? We're going to do f of x, subtract f of a, and then divide that by, now we do the x coordinate. So this minus this, so x over a. This should give us the slope of the line connecting these 2 points. But now we need to make it the calculus. So, Matthew, are you there?
Yes, I'm here.
How do we make this calculus now? If we want to know what's happening exactly at A, then I don't want this X here, right?
Mhm.
So where do I want to move that X to?
Would you have to set a limit first?
That's right. So remember on like this problem. So in this problem, we started at -1 and we said, okay, here's X, and then we want to move that X towards -1. The one before that, we were here at 3, and then we picked an X and moved that X towards the 3, right? So here, if we're here at X and we want to move that towards A, how could I write that, Matthew, as a limit? Limit
X approaches A.
X approaches A of this
Get the equation.
thing here. And this, everybody, is the master formula. If you want to know the instantaneous rate of change of a function at some value A, then you need to calculate that limit. If you can calculate that limit, you're in business. And later on, we're actually going to call that the derivative, but right now we're just going to leave it alone. All right. So I'd like for us to do an example. Well, you know what? Let's define it right now. Okay. This thing is used so much. Okay. This thing is used so much in calculus. We have a special notation for it and a special name for it. This thing is called the derivative of f at A. And we have a special notation for it. Here's the notation we use. F with a little, what do they call that? When you do like an apostrophe at the end of a sentence?
They call it
Yeah.
prime.
But here we call it a prime. A prime. We write F prime and then we put A. So that is notation for this. So that really just means take the limit as X approaches A of f of X minus f of A over X minus A. The sooner you memorize that, the happier you're going to be. Let's do an example. New example, brand new problem, all right?
Sir, quick question.
Mm-hmm.
We're supposed to do 2.1 for homework, right?
Well, you're supposed to try it. We just started 2.1 tonight or today. So
I was trying it all night last night.
Ryan, I told you, remember, only do what the sections we've covered, right? Last time we did continuity, right? Last time we did continuity. And we were just starting 2.1 last time. So after today's class, you should be somewhat okay with 2.1. I still think you're going to have issues because I've really kind of taken my time through this.
Bring it on.
Let's do an example. So,
At least you tried.
what's that?
Oh, actually, I was telling Brian, at least you tried.
Yeah. All right, so here we go. I would like for us to do the following. Now, we're going to put everything that we just have learned together, all right, in one problem. Find the equation of the tangent line to the curve. I'll just make one up. Y equals x squared plus 3x. Let's just stick with that. At the point 5, let's see, 40. All right. Everyone got that written down? X squared plus 3x. I'm just going to take a look at this real quick, this graph. X squared plus 3x. There it is. It's a parabola. Keeping things kind of boring right now. Here's a parabola. And if we go to 5, 5 is right here. It's way up here at 40. So I'm going to zoom out. There we go. So at 5, we're way up here at 40.
I have a question.
Yes.
For the test, are we gonna have a graph?
No. You won't need it though. I'm just trying to give you a visualization of what we're doing. Okay.
Okay.
So the question here is asking us to find the equation of the tangent line to the curve. This is the curve, and then this was the point. So when you look at this curve, there is a line that is tangent to it that just touches through that point like this, right? Just touches through that point. And we're supposed to find the equation of that line. Somebody in here tell me, what information do you need to find the equation of any line? So if I ask you to find the equation of a line, what are the 2 pieces of information you must have?
The slope and 2 coordinates.
The slope and
A limit?
point, or 2 points.
2 points.
So it's either one. If someone gives you 2 points, you can find the equation of a line. If somebody gives you a slope and a point, you can find the equation of a line. We're supposed to find the equation of this line. So do you know a point on this line? Do you know a point on this line? Hint, hint. Hint, hint. Do we know that point?
540.
That's the point 540.
540.
Good. Now, do you know the slope of this line?
You need one more point.
Kind of.
Do you mean the slope of what we have with the 5 and 40, or the slope of the tangent line?
The slope of the tangent line.
Oh, okay.
So look, the slope of the tangent line is exactly the instantaneous rate of change. It's what we have been just doing in the last few problems. Okay, when we were talking about this, instantaneous rate of change, okay, when we've been doing this, what we've been finding is the slope of the tangent line. That's what we've been doing. I was trying to see if you could make that connection. Might have pushed a little too hard here.
So do we just plug in 5 for the equation?
Well, we're going to do a couple things. First thing is to find the equation. Oh shit. To find the equation, right? Oh my gosh, stop it. To find the equation, we will need a point, which we have, check. The next thing we need is the slope of the tangent line. And for that, we will use limit x approaches a, f of x minus f of a over x minus a. We will use the formula we just came up with to get the slope of that line. Let's work through this one, and then once we get through it, we'll do another example, and hopefully you'll start to catch on to how this is going to work overall. All right, let me go back to this.
And the question you're asking, basically translating to find the equation of the derivative, or
no?
Is that what it's saying? No.
We have to have. Okay, let me do this. Let me do this. I'm thinking, hold on, of how I want to do this. When you have a graph of a function and you go to some point A and you go up there, I just told you that the instantaneous rate of change was going to be equal to this limit. What that means geometrically is that we are finding the slope of this red line, which is the tangent line. So not only is this the instantaneous rate of change, it is also the slope of the tangent line. I'll put slope and then put a little tan underneath so you know I'm talking about the slope of the tangent line. So this limit also gives you the slope of the tangent line, which represents the instantaneous rate of change of the function at that point. Now, if we establish that, then doing this problem, saying find the equation of the tangent line, to make it easier, let's just change it to find the slope, okay? And then we'll do the other problem afterward. Just change this to find the slope of the tangent line to this curve. So in order to find the slope of this tangent line, here's what we have to do. We just have to use the formula. The slope of the tangent line should be the limit as x approaches a of f of x minus f of a over x minus a. Now, for us here, what's a?
5.
5.
5. Okay, a is 5. That's the x coordinate that we're approaching. So if you go back to that picture we had of the graph, 5, right? We had 540. So we're going to be approaching 5. So that's your a. Okay. Let's see if we can figure this out. This is equal to limit x approaches 5 because a is 5. Okay, what is f of x? I'm trying to do this top left corner right now. What's f of x?
The equation itself.
Just the equation itself, x squared plus 3x. Okay, minus, now what is f of a?
40.
Well, that's just plugging what into this thing?
5.
5. Plug 5 into this, and you get 40. We know that because of this point, right? And then divide that by x minus
5.
5. Now, if you check right now on this limit, you're going to get 0 over 0. If you try and just plug in 5, you're going to get 0 over 0. So you have to do some algebra first. Does that factor up top?
Yes.
What is it?
X plus 8 and x minus 5.
Okay, and when you do that, the x minus 5s will cancel, won't they?
Yep.
And now you can let x approach 5 and you get 13. So what we're saying now is that if you were to go to this graph, if you were to go to the value of 5 and go up here to where it hits the graph up here at 40, and then you were to draw the tangent line that goes through that point, what we have discovered is the slope of that line is 13. That's what we just discovered, all right? Any questions on that? 13 is also what we would consider to be the instantaneous rate of change at that point. So at 5, the function is changing at a rate of 13. That could be 13 miles per hour, 13 feet per second. It depends on how we're measuring things, but in general, it's just a 13. Okay. We need to answer the original question. It was not the slope. I want to know what the equation of the tangent line is. So let me take this.
How'd you get 40 for the top?
Right here?
Yeah.
So that's f of a. That's this, right? Which is really just, a is 5, right? So it's whatever happens when we plug 5 into the function. And if you plug 5 into here, you should get 40. So 5 squared plus 3 times 5. 25 plus 15 is 40. I'm not sure who asked that, but is that okay?
Yeah, it's Vivian.
Okay,
Okay, got it.
good. Okay, so right now, just calculating this thing, this limit gives us a number, and that represents the slope of the tangent line. But if I wanted to know, not slope, but if I wanted to know the equation of the tangent line, that's more. The slope is the slope, but to find the equation, you need more. So to do this, you actually have to go back to college algebra, and you have to go back to this formula. We're going to use this formula a lot now. So remember that formula from college algebra. This is what we call in college algebra, the point slope form of a line, or sometimes it's called the point slope formula. Does that look familiar from college algebra?
Yes.
Yeah.
Hey, Professor, just a quick question. Since we had these points right here, like 5 and 40, why didn't we just plug these points into this equation y equals x squared plus 3x first, and then to rise over 1?
I know exactly what you're saying, because this is actually a point on the graph. It is not an interval. So what we're not doing this. We're not looking at 5 and 40 and then finding the points and finding the slope. What we're doing is we're looking at the point on the graph. Has nothing to do with 40 over here. It's when you plug in 5, you get 40. So
Okay,
we're
got
looking
it.
at that
Thank
single
you.
point and trying to find. That make sense?
Yes, sir, it does. Thank you.
Okay. Uh-huh. I really do wish that we use
So
different notation.
how do we know like which one is an interval and which one is a point? So interval has kind of like different parentheses to it.
Yeah, I was just about to say, this is one of the places in math that I absolutely hate our notation, because there is no way to distinguish this from an interval and a point. Right? There's no way to distinguish it. But if I'm asking you to find the equation of the tangent line to the curve here at this point, right, at this, I wouldn't say at an interval. I would say at a point. If I were talking about an interval, I'd probably say something like on an interval.
Okay, got it. Thank you. Just want to make sure.
That's a good question. Yeah.
I have
Okay.
a question too.
Yep. Uh-huh.
Oh, sorry.
No, that's all right.
I'm guessing we might try to find a point, but for the point slope, can we just do the 5 and the 40 and 0, 0, or would that not work?
You'll want to use this point. Absolutely. You don't.
Yeah,
So you
but
really
like
don't.
I'm talking for like the other.
Yeah.
For the other coordinate, could we use 0, 0, or do we have to do algebra to find another point on the?
No, you have to use this point. You have to. And the reason you have to use this point is because the instructions are to find the equation of the tangent line to this curve at this point. So when we look at this picture and we draw our tangent line here, here's the point 540. When you draw this tangent line right there, this is the only point that is on that line. You see what I'm saying? Like 0, 0, like this point right here is not on our line. So you can't use 0, 0. You have to use that point. Braxton, is that okay?
Yeah, that's good. I'm guessing you're gonna show us like what else to use for the point slope formula then.
Yeah, I'm not done. I haven't finished. I got a bunch of questions, so I had to stop. So I'm ready to finish this off. I'm going to use this formula, right? I know what the slope is. The slope is 13. And the point is just the point that I was given, right? 540. So I'm just going to plug things in. I should have y minus the y coordinate up there is 40 equals 13. And then I should have x minus 5. And that's it. That's the equation of the line. Now I'm going to simplify. I'm going to multiply through. So y minus 40 equals 13x 65. And then I'll add 40 to both sides. If I add 40, I should get negative 25. There it is.
Quick question. So on tests and quizzes and such, is it okay if we just plug it in and leave it, or do you want to simplify all the way to?
You mean like distributing this through
Yeah.
and like cleaning it up? I wouldn't mind on test if you left it this way, but later on, we're actually gonna wanna do something with this. So you're gonna have to solve for y eventually. So you may as well practice while you're doing these, just solving for y. It won't hurt. It's just good exercise for you for later. Okay, let's see if we got the answer right, okay? And maybe when I do this, you'll see it all come together, right? We were given this graph, right? Let me try and zoom in on this a little bit. We were given this graph, and we were told to go and find the equation of the line that goes through, the equation of the tangent line that goes through that point, right? That's what we were told to do. And we just came up with an answer. The answer we came up with was y equals 13x, what was it, minus 25? Minus 25, there we go. I just typed that into the computer, and can y'all see that we got the right answer? Can y'all see that that line goes through the point? It's hard to see it, but it goes through the point 540, and it's tangent to that curve. Are you convinced?
Yeah.
Yes.
Can you change the color from black to something else that's more like,
I probably can, but I have to hit the right buttons. How about dotted? Ooh, dotted's good. Okay. All right, we have about 12 minutes. Let me try and do one more. Okay, let me try and do one more. Same instructions, all right? I want to find the equation of tangent line to this curve. I'll write it as a function this time instead of y equals. I just put f of x equals, let's go 2x plus 1 over 3 minus x at the point 2, 5. Would y'all like to see the graph of this function first, or you just want to go after it?
I want to attack it.
Go ahead and go for it. Okay, so I need the equation of the tangent line, right? So that tells me I'm going to need to use y minus y1 equals m times x minus x1. What part of this do I know?
You know the y and the x right now.
We know the x and the y, right? We know that the 2 is the x1 and the 5 is the y1. So we can actually write this down right now if we wanted to. The only thing I'm missing is the m, right? I just need the slope of that tangent line. But the slope of the tangent line is going to come from the formula that we've spent most of today trying to come up with, which is this formula. Right? That's the formula we're going to use for this. Now, what is the a for us here, though?
2.
2. A is the 2. So this number right here will always be that number here and here and here. So let's plug that in. We get limit x approaches 2 of f of x minus f of 2 over x minus 2. All right, you have 5 minutes to work in groups. I'll just break you out real quick. Y'all can talk to each other or not. It's up to you. I'm going to give you about 5 to 6 minutes to see if you can algebraically simplify that expression, and maybe someone will have an answer at the end of 5 or 6 minutes. I think you're probably going to run into some issues. See how it goes. Okay, we should all be back here now. So what did y'all run into there?
Didn't get to finish.
Okay.
I ran into a 0 over 0.
Okay, let's take a look at it.
Yeah, that's what I got too, 0, 0.
Okay, so you should, here's the formula. We replace the A's with 2. And then you have to figure out, what's f of x? Well, that's just the original function. And then f of 2, we know that that's 5. So we plug in 5 here. And then the bottom is x minus 2. So here's where you should have been. Now, if you try and take this limit at this point, you will get 0 over 0. So that's bad, right? And that means it's algebra time. And I promised you at the beginning of this semester, I said calculus is algebra on steroids. And this is it. I mean, now you've got to do algebra to make this thing work. So what I did is I took, because this was a complex fraction, I took those two and put them together with a common denominator. So I multiplied this 5, I looked at it as a 5 over 1, multiplied by 3 minus x on top and bottom. And then I put these two together to give me this. And then I distributed the negative 5 through to give me this. And then I clean that up. I know I'm going fast through this. Then I clean that up and I got this. And then I realized that if I factor a 7 out of the top, I get an x minus 2 on top, which cancels with the x minus 2 on the bottom. And that leaves you with just the 7 over 3 minus x. And now when you take the limit as x approaches 2, you get 7. And then you take that back up here and you plug that in for m. And when you plug that in for m, you get the final answer. Right here. Now I know I'm out of time, but I'm going to show you this real quick. I want to show you what we just did, 2x plus 1 over 3 minus x. So we did 2x plus 1. Whoa. Okay, whatever. Oh my gosh. All right, here we go. 2x plus 1 over 3 minus x. So here's the graph that we are looking at. And we were looking at the value of 2, what was it, 2.5? Right, that was the value, 2.5. That point right there. And we were trying to find the equation of the tangent line that went through that. And I got y minus 5 equals 7, x minus 2. There it is. Y'all see that? We found the equation of the tangent line that goes through that point. So the moral of the story here is that we have a basic formula. Okay, here's the master formula to find the slope of the tangent line. Now it comes down to algebra. Every problem is set up the same way. You're going to run the limit, and then you're going to get bad. You're going to get 0 over 0, and then you have to be able to execute the algebra to get to a final answer. And then you can take that and plug that in for your slope. Does that make sense?
Yes.
Okay, so the algebra is what's going to start to become hard, all right? Because the functions are going to get more and more complicated. So here's what I'd like for you to do for homework. Just completely ignore. Brian, are you listening? Okay, for homework, only do the stuff from 2.1. I don't want you to do anything on this right now. Well, I do, but just ignore this for right now. I want you to do problems 1 through 6. Okay, 1 through 6. And I don't even want you to pay too much attention to the directions because they'll confuse you. All I want you to do, they're going to, on each one of these problems, they're going to give you a function, and then they're going to give you a point. Okay? They're going to give you a function, a point, just like the problems, the 2 problems we just did. Follow the same thing we just did in class. All right? Find the equation of a tangent line by doing this procedure, right? They give you a function and a point. So you know that the equation tangent line has to look like this. Plug in the points to get your y1, x1, and then go find m by doing the limit. That'll be your homework. We'll come back and we'll finish up 2.1 next time. And it's okay that we took all day to do this and we still need more time because this is a vitally important section. If you can't do this, not much is going to go well the rest of the semester. So, okay. All right. Y'all have a good weekend. When's our test?
You
Next
said
Tuesday.
it was next week.
I think you said you're gonna push it to the 18th instead of 16th.
Yeah, so let's go definitely 18th on that. It will cover 2.1, but only what we've gone up to through today. So on the test next week, I would expect to see me give you an equation with a point and you find the equation of the tangent line. Okay. I will try and send a review out tomorrow. Okay. I'm getting my second COVID vaccine tomorrow, so hopefully I'll have no reaction to it and I'll be okay. If I'm okay, then I'll send out the review tomorrow.
We'll pray for that.
Okay. Thank you. All right, any questions?
I had a question. Yeah.
Yeah, you're free to go.
What
You're free to go.
What does it mean by the slope of a secant line? Like what even like what's the diff? What do you?
He told us that tangent has only 1 point and secant has 2 points.
Yeah,
So like it will be touching 2 points instead of for 1 point.
Exactly, but the thing here is this: what we're doing is we're trying to figure out what's happening at this point A, right? So our technique, our procedure is to pick some other point to the right of it called X, and then what we do is we slide that point over, right? So if you look at this, this is rise over run. Do you agree, Danielle, that that's rise over run?
Huh?
Yes?
Yes.
Okay, that would be, this right here would be the slope of the secant line because you're not moving X towards A. You're just leaving X wherever X is. So that's the slope of a secant line. The only difference between the slope of a secant line and a tangent line is that the slope of the tangent line, what you do is you take the limit as X approaches A of that same expression. So the big difference between secant and tangent line is the limit. If the limit's not there, then you're just going to get some number, some answer. You'll never get 0 over 0. It isn't until you let that X slide over towards A that you actually get a 0 over 0 that requires algebra. Does that make sense, Danielle?
I just said it was just curiosity. That's all.
Okay.
Like I get how to do the limit and stuff like that. I was curious.
Okay.
Thank you.
You're welcome. Any other questions?
Professor?
Okay.
How many derivatives are we gonna go up to in this class? I remember when I took calculus in high school, I think we went up to like the 3rd derivative, but I've kind of forgot how to do it since senior year of high school.
Well, if you've seen it in high school, then you know that eventually we're going to have a much easier way to find derivatives. Like we'll use shorter, like shortcut rules. Like for example, if we want to find like x squared minus 3x plus 2, if that's our function, if you've taken calculus, you know that to find the derivative of that function, all you do is bring the 2 out, and then that becomes minus 3, and then derivative constant is 0. So we get this quick answer. Does that ring a bell, Bryson?
Power rule.
That's called the power.
Yeah, it's familiar.
Yeah,
I
so
don't know. It's just been so long since I did it. I kind of forgot a few things.
yeah, so doing like in this class, we will definitely spend a lot of time with the 1st and 2nd derivatives. There will be a few problems where we go 3rd, 4th, 5th derivative, but really just a few. So focusing mostly on the 1st and 2nd derivative, because those make have the most meaning to us.
What do you mean by 2nd derivative?
Don't worry about it. Not yet. So
Yeah, no.
the question is being asked by somebody who's seen calculus already, some of it in high school. So we're talking about things that are coming later.
Got it. Well,
Yeah,
I
don't
know
wanna get
that
ahead
of
of
it, but I don't know touch that.
Yeah,
I can,
don't worry about it.
oh, I'll text you.
Professor, I have a quick question.
Yes.
In the function, like you said that whatever number we plug in the x is going to be equal 1. Is that correct?
Wait, say that again. In the what?
In a function, like whatever number we plug in the x, is that always be equal to 1?
When was it equal to 1? I'm not quite sure what you mean.
It was you was explaining something like about when we have 0/0 in a function.
Oh, is that when I was showing the difference between those two functions, f and g? Like when we cancel, it's always 1. Is that what you mean?
And that one, like in that page. That was what I understood, but I don't know if I'm correct. Like you put f of x equal 1 and then f for
I'm just not following your question.
I think she's probably talking about that formula sheet we had. That 0/0 is something we have to take limit, and there was some at point. Let's say that number goes to infinity, and if they both goes to infinity, then answer is gonna be, I think, something. It was a specific number. I think it was a 1 or infinity.
Is that what you're saying, Daniela? Or are you talking about something?
no. It's just because I hear that you say that whatever, like, it's, I don't know how to explain. Like, whatever number we plug on the x is going to be equal 1, like how you put in the left side.
I don't know. I'm struggling to understand your question. So
Okay,
is
it's
anyone?
fine.
Yeah, I'm sorry. Are you talking about this specifically right here?
Yeah, the left side,
Okay.
that one.
I just said, hey, everyone, I'm going to just come up with a function. Okay, here it is. The function is this function. I just made that function up. Okay, I said the function f of x is equal to 1. So that means that I defined it this way.
Okay.
I defined it that way. I just said, hey, that's it. So if you plug 4 in, it's going to spit out 1. You plug in 2, it's going to spit out 1.
Okay, I got it.
And what I was trying to get people to see is that if you compare that to this function, that a lot of people think that they're the same function because you could just cancel the x minus 2's, and that would just cancel out and give you 1. So that basically they're the same function. They both spit out 1.
Yeah.
But they don't, because even though you can plug 4 into both of these and get 1, you can't plug 2 into this one. So all this was to illustrate that when you define a function, if you come in here and do some algebra, you have to pay attention to what you're canceling, because you have to avoid that later on. Like you have to make sure you don't accidentally plug in a number that would have made the function undefined to begin with.
Yeah. Okay. Thank you.
Okay. All right. All right. I think I'm going to need to run. So.
Thank you.
Okay.
It was fun. Thank you.
Good weekend.
Bye. Have a good weekend. All right.
You too. Bye.